Dear students, in the lecture 1 of quantum mechanics, we discussed about de Broglie hypothesis, properties of matter waves, expression for de Broglie wavelength in terms of kinetic energy of the particle, and accelerating potential, V group and V phase velocity definitions. In the lecture 2, we discussed about relation between group velocity and phase velocity, group velocity and particle velocity, and Heisenberg's uncertainty principle and its application, that is, non-existence of electron inside the nucleus. In the present lecture, we are going to derive Schrodinger's time-independent wave equation for matter waves. Schrodinger wave equation. With every moving particle, there is a wave associated. We explain the wave motion of a particle. You have to write a equation of motion for it. That equation of motion is written by Schrodinger. There are two types of Schrodinger equations are there. Schrodinger's time-independent wave equation for matter waves and Schrodinger's time-dependent wave equation for matter waves. Here in our lecture, we are going to derive Schrodinger's time-independent wave equation for matter waves. This equation, there are different methods for solving. To derive this equation, we are having different methods. But in the present lecture, we are deriving the Schrodinger's time and wave equation by using general wave equation of a wave. The general wave equation of a wave is given by D'Alembert. The D'Alembert general wave equation is given by dou square y by dou x square equal to 1 by v square dou square y by dou t square. Here, v is the velocity of wave and y is the displacement at any instant. If you solve this equation, we will get a solution for the wave propagating here. But in case of matter waves, we are replacing this y with psi, that is known as a wave function. This can have all the information about the system. And this v, in this equation, this v is the velocity of wave. But in the de Broglie hypothesis, we have mentioned de Broglie wavelength lambda equal to h by mv. In this case, m is the mass of the particle and v is the velocity of the particle. So we can't use v is the velocity of matter waves. So that's why we are using w is the velocity of matter waves. So now by replacing y with psi and v with w, the wave equation of a matter wave can be written as dou square psi by dou x square equal to 1 by w square dou square psi by dou t square. This is the general wave equation of a matter wave. Here psi is the wave function, w is the velocity of matter waves. This is the case of one-dimensional. In case of three-dimensional, here we are getting dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z. In case of one-dimensional, this psi is the function of x and t. In case of one-dimensional, psi is the function of x and t. If we take three-dimensional, then psi is the function of x, y, z, and t. So now we have to derive time-independent Schrodinger equation. But in this case, psi is the function of x and t. So we have to eliminate this t. Then you will get the Schrodinger's time-independent wave equation. So the general solution of this equation can be written as the psi equal to psi naught into e power I omega t. So the general solution of this equation can be written as psi equal to psi naught into e power I omega t. This psi naught is not a constant, it is a function of x. Psi naught is a function of x. So now we are differentiating this psi with respect to time 2 times. Then we are replacing this dou square psi by dou t square with the corresponding value what we are getting here. So if you differentiate first time, then dou psi by dou t equal to psi naught into e power I omega t derivative e power I omega t into this I omega derivative I omega. I is the complex number, I square equal to -1. Then again, if you differentiate with respect to time, here dou square psi by dou square equal to psi naught is a constant with respect to time, but it is a function of x. And e power I omega derivative e power I omega t. And again I omega, but I omega I omega is already there, so that this becomes I square omega square. We already discussed I square equal to -1. So -1 into omega square minus omega square psi naught into e power I omega t. So psi naught into e power I omega t is nothing but psi. Okay, so we can replace this psi naught into e power I omega t with psi. Then this equation becomes dou square psi by dou square equal to minus omega square psi. So this value of dou square by dou square we are substituting here in this equation. Then this equation becomes dou square psi by dou square equal to 1 by w square minus omega square psi. So this equation becomes dou square psi by dou square equal to 1 by w square minus omega square into psi. We know omega is the angular frequency which is equal to 2 pi into f. So we are replacing this omega with 2 pi into f. Then omega square becomes 4 pi square f square by w square is already there into psi. We know f equal to the frequency equal to velocity by wavelength. So in case of matter waves, the frequency of matter waves equal to velocity of matter waves by wavelength of matter waves. So we can write f equal to velocity of matter wave, we are able with w by lambda. So replace f with w by lambda. Then this equation becomes 4 pi square, f is w by lambda, so w square by lambda square, and already w square is here, and psi. So now these two are cancelled here. So w square will cancel. Then that equation becomes dou square psi by dou square equal to minus 4 pi square by lambda square into psi. We know lambda is the dipole level and is equal to h by mv. So we are replacing lambda with h by mv. So lambda square becomes h by mv whole square, that is h square by m square v square. This m square v square will come here. Then that equation becomes dou square psi by dou square minus, I will take it left hand side, that becomes plus 4 pi square. This m square v square will come here. Then 4 pi square m square v square by h square psi. Now let us take E is the total energy of the particle and V is the potential energy. Then E minus V gives the what value? Kinetic energy. Let E is the total energy and V is the potential energy. Then E minus V gives the kinetic energy. So let us take E is the total energy, V is the potential energy, then kinetic energy equal to E minus V. We know the kinetic energy equal to half m square. Therefore, E minus V equal to half m square. We will multiply both sides with 2m. So 2m into E minus V equal to 2m. If you multiply, the 2 will cancel. This one becomes m square V square. So multiply both sides with 2m. So 2m into E minus V equal to this 2 will cancel m square V square. So in the previous equation, there we are having this m square V square. Now we are replacing this m square V square with the 2m into E minus V. So this m square V square we are replacing with the 2m into E minus. So m square V square we are replaced with 2m into E minus V. Then that equation becomes 4 pi square 2m into E minus V by h square into psi equal to 0. Then 2 into 4, 8. 8 pi square E minus V by H square. So the final equation becomes dou square psi by dou square plus 8 pi square M E minus V by H square psi equal to 0. This is the Schrodinger's time independent wave equation in one dimensional. So if you want to get three dimensional, we have to write dou square in place of dou square to dou x square. We have to write dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square. In this case, psi is the function of x, y, z. We can replace this dou square psi by dou square plus dou square psi by dou y square plus dou square psi by dou z square with del square psi. The del square is a Laplace operator. So this can be replaced with del square psi. This del square is the Laplace operator. So by replacing this dou square psi by dou square plus dou square psi by dou y square plus dou square psi by dou z square with del square, then the equation becomes del square psi plus 8 pi square m into E minus V by H square psi equal to 0. So this is the Schrodinger's time independent wave equation for three-dimensional. Okay, this is the Schrodinger time independent wave equation for three-dimensional case. If you take a free particle, if the question asks you find the Schrodinger time independent wave equation for free particle, in case of free particle, what about potential? Potential becomes 0. So if you want to derive a Schrodinger time and wave equation of free particle, then in that case V equal to how much? 0. So put V equal to 0, then the equation becomes dou square psi by dou square plus 8 pi square m E by square psi equal to 0. So this is the Schrodinger's time independent wave equation for a free particle. So in case of free particle, this is the Schrodinger's time independent wave equation. So in case of three-dimensional, we can write in this way. In case of one-dimensional, we can write. So next, we are going to discuss about the physical significance of a wave function. If psi is the wave function of any system, any microscopic system, and psi star is its complex conjugate, because most of the cases psi is complex in nature. So if psi is the wave function and psi star is its complex conjugate, then psi into psi star gives the probability of finding the particle at any instant and at any position. So we are able to locate the position of the particle by knowing the psi star. So we can able to locate the position, then we can estimate about the remaining properties of the system. So that is the physical significance of wave function here. If psi is the wave function, psi star is its complex conjugate, then psi into psi star gives the probability of finding the particle at any position at any instant. And it is also gives the probability density. For suppose if you want to find the position of particle in the small volume dx, dy, dz, then what is the probability? The probability to finding the particle in the small volume is multiply this probability density with this value. So that becomes modulus of psi whole square dx, dy, dz, or psi star equal to dx, dy, dz. So this is the probability of finding the particle within this volume here. If you want to find the position of the particle throughout the system, or suppose that means we are integrating from minus infinity to plus infinity, then that will give the total probability. The total probability is always equal to 1. This integral minus infinity plus infinity psi star dx dy dx gives the what value for you? The probability of finding the particle within the system, total system. If particle exists in the system, definitely we can find the particle. So the total probability definitely equal to 1. So this integral minus and plus infinity psi star dx, dy, dz gives the total probability. It should be equal to 1. If it is equal to 1, then psi is called normalized wave function. If it is equal to 1, then psi is called normalized wave function. Normalized wave functions only can explain the system completely. Normalized wave functions only can explain the system completely. So psi always normalized. If it is not normalized, first you have to normalize the wave function, then use the wave function to explain the system. In addition to this normalization, it has to satisfy some conditions, those we named as limitations of wave function. That is, psi must be finite for all values of x, y, z. So psi should be some finite value. That means we are able to define that value, well-defined value. So we should have well-defined value for psi at a particular instant. And psi must be single valued. That is, for each set of values of x, y, z, psi must be only one value. Okay. So for one set of x, y, z values, psi must be only one value. It should not be have the more than one value for a same set of x, y, z. For example, if you take a size function of x only, size function of x only, for suppose. So this is the psi x value, and this is the psi of x. Psi is the function of x only. This is psi of x, and this is the x here. So if you take the psi of x is like this, for suppose. So then if you observe here now, the same x value, we are having two psi of x values. So this is not allowed. So then psi is not a single value. But if you take the system like this is the x value and this is the psi of x here. And this is like this. So for any x value, the psi x is only unique. There is only one value for a psi of x. But you can have the same psi of x value for different x values. That is allowed. For different x values, you can have the same psi of x value. But same x value, you can't have the more than one value for psi of x. So that is the explanation about the single value. So psi should be single value. And next is psi must be continuous for all the rate. So it always continues here. So that is another important characteristics of a wave function. So psi must be continuous for all regions except in those areas where the potential barrier is infinity. The potential is infinity, there is a chance to discontinue at the loop. So other than that, always psi should be continuous. So, and first derivative of psi also continuous. That means dou psi by dou t and dou x by dou t. That should be continuous here. So this continued for suppose if we take this the barrier here, then this is the wave function psi x. Then after that it will continue like this. That means at this boundary, and here it is psi 1, and here it is psi 2. And this boundary is for suppose a. The psi 1 at x equal to a equal to psi 2 at x equal to a. That means there is a continuity in this wave function. That is allowed. And if the situation is like this, for suppose this is the psi 1, and here this is the psi 2. So at this boundary, at x equal to a boundary here, if you observe here, this is x equal to a boundary here, for suppose. Here this is the psi 1 value, and here the psi 2 value at the same value of x here. That means there is a difference here. So it is discontinuous here. So this is not allowed here. So this is allowed. So if this situation will happen only when this barrier is infinity, this potential is infinity, then only this is allowed. So like that, the first derivative of psi is also should be continuous. Next, we are going to discuss about eigenvalues and eigenfunctions here. We know in the quantum mechanics, no physical quantity can measure absolutely. So no physical quantity can measure exactly. Not possible. All are expectation values only. But how to get these expectations also? To get these expectation values, we are using operators in quantum mechanics. So in the quantum mechanics, operators are observable quantities. For every physical quantity, we have an operator. For every physical quantity, we have an operator. When these operate on wave function psi, we can get the expectation values for the corresponding physical quantity. If it is a momentum operator on wave function psi, we can get the expectation value for moment. If it is a kinetic energy operator on wave function psi, we can get the expectation value for kinetic energy. So in this way, we can get the expectation values for every system if you operate these operators on a wave function psi. So that's why in the quantum mechanics, operators are observable quantities. Once you are getting the expectation values, then we go forward with those expectation values. Results are current, then the expectations are correct here. So here I will give some examples of operators here. So one is momentum operator. So this is the momentum P cap. We are representing the operators with cap area. P cap. So P cap equal to minus IH class dou by dou x. If we operate this one on the wave function psi, we can get the expectation value for a momentum. Like that, kinetic energy operator is the h class square root 2m dou square psi by dou square. If you operate this operator on a wave function psi, we can get the expectation value for a kinetic energy. So these are the total energy operator. Total energy operator is also known as Hamiltonian operator. So let O cap is the quantum mechanical operator. That may be a momentum operator, that may be a kinetic energy operator, or total energy operator. If this O cap is operator on wave function psi n, and n is the different state represents here. Say n equal 1, that is first state, n equal 2, second state, like that. So then O cap is the quantum mechanical operator on wave function psi n, corresponding to a state n. Then On psi n is equal to some an integer value into psi n here. So this an gives the expectation value for the corresponding physical quantity. So here this O cap is kinetic energy, then an gives the kinetic energy values. This O cap is momentum operator, then an gives the momentum values. This O cap is total energy operator, then an gives the kinetic energy expectation values. So these expectation values are called eigenvalues. So an gives the eigenvalues, and this psi n is the state function or eigenfunction. So n equal to 1, the wave function in the first state, n equal to a function in the second state. So this psi n represents the eigenfunctions, an represents the eigenvalue. So psi n is the eigenfunctions and an is the eigenvalues. This lecture we will stop it here. In the next class, we are discussing about one of the application of Schrodinger wave equation. We are writing a Schrodinger equation for a system and how the behavior of a particle can be explained by using Schrodinger wave equation. We will discuss in the next class. Thank you.